Hello and welcome again to the lecture course on Relativity and Cosmology. Last time I introduced to you rotating black holes, which are the realistic black holes for astrophysics. And we have seen that there's an exact solution, an exact vacuum solution of the Einstein equations for axial symmetry. And this is the Kerr solution that I wrote down and discussed. Now, before we go on with further properties of the Kerr solutions, the ergosphere, the Penrose process, I would like to have here a subsection discussing the motion of geodesics, time-like and like geodesics in the Kerr geometry. Because this is important for observations. Because what you observe is, of course, typically not the black hole itself, but bodies or light rays in its vicinity that you observe and which move on geodesics mostly. Here in this subsection I follow Hartel's book on gravity, so you can read about that in detail in that book or elsewhere. You recall from chapter 9 the geodesics in the Schwarzschild solution, which we used to discuss light deflection, perihelion motion of Mercury, and other things, and the Shapiro time delay. Now, as you can imagine, because the solution here is much more complicated, also the geodesics are much more complex than in the Schwarzschild case. In the Schwarzschild case, we made use of the conservation of angular momentum for a test particle, which guarantees that the orbits, as in classical mechanics, stay within one plane. So we had one plane, and there the motion took place. Now here, that's no longer true. General orbits do not stay in one plane, except those which start in the equatorial plane. Now you have the axial symmetry, and you have the equatorial plane at theta is pi over 2, and those which start in that plane, and they will stay there, since the angular momentum conservation holds with respect to the symmetry axis. We restrict here in this subsection to that case only. For the general case, I have to refer to the specialized literature, in particular Chandrasekhar's book, where you can find all the detailed calculations. So, general orbits do not stay in one plane, except those which start in the equatorial plane at theta is pi over 2. Because of the symmetry of the Kerr metric under theta going to pi minus theta, the corresponding component of the test particle's angular momentum is conserved. So we restrict to this case here, except those which start in the equatorial plane. So restrict here to this case. Now I do not write down the full Kerr metric again. It was written down last time, but I write down, how it looks like at on the equatorial plane. So so Kerr metric for theta is pi over 2. Then we have the following expression. So you can easily check that by just inserting that particular value, which is minus 1 minus 2m over r dt squared minus 4am over r dt d phi plus r squared over delta dr squared plus r squared plus a squared plus 2m a squared over r d phi squared. Where the delta here is r squared minus 2mr plus a squared. Okay, still has a couple of terms, but it's much simpler than the full Kerr metric. So that's what you use for the following discussion, which I will not do in all the algebraic details, but you can easily check this by using this expression. If you recall the situation for the Schwarzschild metric, there we made use of conserved quantities, I mean the angular momentum and the energy per unit mass, and we do the same here. I mean, angular momentum here, of course, for those orbits is with respect to the symmetry axis only, but this is what all we need, conserved quantities. So we called it F and L. So F was minus psi times u. I mean, this was the Timelike killing vector psi, and the 4 velocity, which is the same as minus g mu nu psi mu u nu. So that's I mean, has the same interpretation as for the Schwarzschild case, so I don't repeat the discussion made there. So that's the energy per unit mass. So it is dimensionless. And here we have, for the angular momentum, we have the second killing vector, the axial killing vector psi, that we multiply with u, which is g mu nu psi mu u nu, and this is the angular momentum per unit mass with respect to the symmetry axis. Now for equatorial orbits, this is of course the total angular momentum. Now, okay, we have this scalar product, so we can express this by inserting here g mu nu. So F, which is this here, and so we insert here in that coordinate system that xi is a 1 0 0 0. So F is a minus g t. So the t component nu u nu, which is minus g, and that's only that coordinate here, minus g t t u t minus g t phi u phi. And similarly here for L. So here we insert the killing vector psi, which is 0 0 0 1. So we get here g phi nu u nu, which is g phi t u t plus g phi phi u phi. Now, so you see we have here two unknown components of the 4 velocity, namely ut and u phi. These are the conserved quantities, so we have two equations for these two components that we can solve for after inserting here the corresponding expressions for gtt, gt phi, and so on. You just take this here, so gt phi, then you have this here, and so on. So solve these two equations with respect to ut and u phi, and insert the Kerr metric for theta is pi over 2. No? And if you do that, that's easily done. When man just two equations for two unknowns, then you get that ut and u phi. No? From this, and ut, of course, you know the 4 velocity is dt over ds, and this is d phi over ds, and it turns out to be that is 1 over delta r squared plus a squared plus 2m a squared over r times f minus 2ma over r times L. And for the phi component, you have here 1 over delta, and this is 1 minus 2m over r L plus 2ma over r times f. Okay, then what we aim at is to find an analogy to the effective energy equations that we already used in the Schwarzschild case, already in classical mechanics. And for this we need a further property, and we have here the 4 velocity, and of course the 4 velocity is normalized to -1. If we restrict now to time-like geodesics, I mean, I will treat the case of null geodesics separately. And yeah, you just write this out. I mean, the corresponding components you have to sum over, I mean, t and r and phi and theta. The theta component here is 0 because we restrict to the case of the equatorial plane. So there's no component of the velocity in theta direction because this is constant. And so the remaining terms then read at gtt ut squared plus 2 gt phi ut u phi plus g phi phi u phi squared plus g r ur squared is equal to -1. Now the ur I have not yet introduced, but ur squared is clear that it's dr over ds squared. Now we insert here the expressions that we have found. So for ut and u phi, and then we get an effective equation that contains a dr over ds squared plus terms that depends on L and psi and so on. So we have u times u -1, then leads to the following, which is then, yeah, I write it in that suggestive form that I divide here by the term, so that the dominating, that the first term is 1/2 dr over ds squared, so the kinetic term per unit mass. So then we have here 1/2 dr over ds squared plus an effective potential depending on r, which is constant, and the constant again is f squared -1 over 2, so that's constant. And so the behavior of the geodesics then follows, of course, from the shape, the form of V effective. Let me write down V effective explicitly, so it's defined as follows. We have -m over r, which is the Newtonian term for gravitational constant equal 1, and then we have here terms L squared minus a squared, s squared -1 over 2r squared minus m L minus af squared over r cube. No. So you see here that this is a natural generalization of the Schwarzschild metric. No? So for a to 0, now recall a is j over m, where j is the angular momentum. I mean, these terms here with a vanish, and you have minus m of r plus L squared over 2r squared minus m L squared over r cube. Now that's the effective potential we had in the Schwarzschild case, which is the Newtonian terms, the 1 over r potential, the centrifugal term, and then the Einsteinian corrections. And you see here, you have similar terms here. It's just that you have here additional contributions from the angular momentum. So you have here this minus a squared term, and here also this minus a term, which means that this here, in contrast to this, depends explicitly on f. And for the Schwarzschild metric, this was just here occurring on the right-hand side. Before discussing this further, let me also write down the the light-like case. Well, I should write down, this is the Schwarzschild case. So for null geodesics, then u times u is 0. So we have u, which is g mu nu u nu is 0. And okay, this is no longer dx mu over ds, but dx mu over the lambda, where the lambda is a fine parameter. So this is g mu nu dx mu the lambda dx nu over the lambda. So, and we now do an analogous calculation as before. So here, so instead of here the -1, you have just here to have 0, and again inserting here the components of the for velocity and so on, and then we find the following. So an analogous calculation leads to the following. So we have can write it in that form, 1 over L squared. Then you have a dr over the lambda squared. So I follow here the conventions of Hartelsbruck in writing these terms. Is 1 over b squared minus an effective potential that we call here W effective, in contrast to V effective. And B is defined here as the absolute value of L over F, and this is called the impact parameter. So they're borrowed from the theory of scattering processes. So that's here the corresponding equation for null geodesics. I have, of course, to write down the explicit expression for W, similarly to here. So W effective of R is 1 over R squared. Then you have 1 minus A over B squared minus 2M over R. Then you have 1 minus, and here I explicitly introduce here the sigma AB squared, where sigma is actually the sign of the angular momentum L. Now you see here that here and as well as here the sign of the angular momentum enters, which is not the case in the Schwarzschild limit. So sigma here is the sign of L, so it's +1 or -1, and so sigma +1 is the case of co-rotation. So when the motion of the particles is with the rotation of the black hole. So this is co-rotation, and sigma -1 is then the counter rotation. If the motion of the orbit is the opposite than the rotation of the black hole. For the Schwarzschild case, I mean, if you have here A to 0, you have 1 over R squared minus 2M over R cubed, which is again what we know from the chapter 9. There's of course no Newtonian potential. You have this centrifugal part, and the Einstein correction. And the L squared is of course here missing because in this form it's divided here by L squared. So that's the Schwarzschild case. Let me emphasize again that unlike in the Schwarzschild case, these effective potentials, they depend explicitly on F and also on the sign of the small l. This is why you have here this difference between co-rotating and counter-rotating, which will be reflected in the behavior of the test particles and light rays. Now for astrophysics, and in the last section in the black hole chapter, I will tell you about observations. So for astrophysics, an important property is a so-called innermost stable circular orbit. Yeah, so that's the orbit that is on a circle, and which is has the smallest possible stable distance to the black hole. And so if you observe this particular orbit, then of course you are as close as possible to the black hole. So important for astrophysics is here the binding energy of the innermost stable circular orbit. Yeah, so the acronym that the astrophysicist uses Isco. I mean, after here these letters. So here, in the literature you find here this acronym Isco. Now, how do you calculate this? Well, the circular orbit. I mean, if you recall here, for example, the Schwarzschild metric here, which has this this shape, and then it's here, and of course you get this by just looking for the minimum of the potential. And similarly here we check the minimum of the potential. So let us do this for V effective here. So circular orbit at R, well, we call that value where the minimum is reached capital R, and of course you get this by dr over S is equal to 0. So that's the condition for the circular orbit. R is constant, so you get that this is and that this is equal to f squared minus 1 over 2. And in addition, of course, you have to look for the minimum, which is the usual equations. No, that the first derivative is 0 and the second derivative is positive. Yeah, and from this, which is a standard calculation, you find then F, L, these two, and also the radius R for this Isco. So if you set the second derivative to 0, then you're just on the verge of being unstable. So I could do that, but it would not be too illuminating to give you a detailed expression. Let me here at the blackboard only consider the simplest case, or depict the simplest case, which is the so-called extremal black hole. So here, simplest case, the extremal Kerr black hole, which is characterized by absolute value of A is equal to M. The simplest case for an Isco. So we have a brief look at the case of the extremal black hole, A equals M, for the Isco. And if you use these equations just for that case, so you set A is equal M, then you find the simple results. So one finds F is just 1 over square root of 3, L is 2M over square root of 3, and R is equal to M. This is for the co-rotating case. I show you a diagram. I mean, for the counter rotating case, it's different. So you will have bigger radii. Yeah, so that's okay for the circular orbit. No? Capital R is the small r for the circular orbit. Now, if you recall our expressions for the event horizon, then you recall, I mean, that for the extremal case, r equal m is the value for the event horizon, right? So this means that the orbits can be very close, in fact, at least in the coordinate distance here, that's the coordinate distance to the black hole. Now, for the observations relevant is, of course, the proper distance. So let us calculate, so this is the coordinate. So, so this refers to the coordinate distance. The proper distance you get from the metric. And so let me just write it here, so the proper distance. If we, for reason of just doing the calculation, write that A is M1 minus delta, so it's a little bit non-extremal, then what you get is that R is M times 1 plus 2 square root of delta. And the proper distance, okay, it is still the coordinate distance, so the proper distance turns out to be the following. So if you take R minus R plus, so that's the value of the event horizon, which is actually M, and you have the proper distance that corresponds to this coordinate distance, then what you find is when you go to the extremal case that you have m times the logarithm of 1 plus the square root of 2. No? So you still have the m here mainly, but of course you get here this numerical factor, so it's a bit bigger. It's really outside outside the event horizon, and but it's still very close to that. Yeah. Now what you have to do, you calculated the proper distance from r is equal to r plus to m to small r is m times 1 plus 2 square root of delta. The binding energy of the orbit per unit mass is, as in the Schwarzschild case, it's 1 minus f, right? So why? So 1 is the rest energy at infinity, which is in a sense m over m. I mean, the rest energy is mc squared, but we divide by mc squared. So that's the rest energy per unit mass at infinity. So m over m, if you like, this is 1. And that's here the energy on the orbit as measured from infinity. Yeah, this was our conserved quantity that we introduced. Now, of course, the f is here 1 over square root of 3. So this means that you get here maximally, in that case, so 1 minus f is 1 minus 1 over square root of 3, which is about 42% of the rest energy can be released. So this is much more than the release of energy that you have, for example, nuclear processes, which are only a few percent. No? So you see, in that case, I mean, if you approach the black hole gravitationally, you can really gain a lot of energy, in principle, by that, because you have this binding energy. Well, realistically, what the astrophysicists tell us, it's of course not quite like that for realistic cases, but it's possible up to 30% still. Let me finally show you two diagrams. So we have here Isco over m, and now this is the result of a calculation, also taken from Hartle's book. You plot it here to A over M. No? So it's not just for the extremal case. And we have here 1, say. And here we have the extremal case 1. And here we have here 9. And here we have the value 6. And so we have here the case, well, it looks roughly like that here for the counter-rotating particle. And what we considered above was the co-rotating case. So it's here, it looks here basically like that. So this is here co-rotating. So for the Schwarzschild case, when this is here 0, we have this value 6, which you recall perhaps from our earlier discussion, Schwarzschild case. Then we have R Isco is a 6m, which is 3 times the Schwarzschild radius, but then it goes down to the value here R, I mean the radial coordinate is equal to m here for the extremal case, which corresponds to that case considered. And the binding energy is the following. So 1 minus F, and you have here A over M, and so here again the 0, and here say we have here 0.1, 2, 3, 4, here is 0.4, so that's the maximum. Well, it's a bit more, we have seen the maximum is 0.42, so we have here 1. So here we have here roughly that curve here for the co-rotating. So that's here the 42%, and here this is basically roughly constant, so in the drawing you will not see the difference, something like that. So much smaller counter, because the counter-rotating case, they will not enter as much as the co-rotating case towards the black hole. Okay, these are just some brief remarks, I would say, about the behavior of geodesics. It has turned out that this is our own special topic that people discuss, both for mathematical, but maybe even more for astrophysical reasons. And research is still going on because it's directly relevant for observations, and it's clear that many numerical methods and computer codes are used for that. And this here is just a case that can be dealt with analytically, but in general, if you have the orbits that go everywhere, I mean not just on the plane, you can do analytic calculation as Chandrasekhar did, but they are extremely complex, and most people actually go to computer calculations. Okay, so far for the geodesics. So next time we will go back to the Kerr geometry and find the most interesting region that is something new and only possible in relativity, so-called ergosphere. The ergosphere is something that is outside the event horizon, which has very bizarre properties. In particular, allows you to, in principle, extract energy from the rotating black hole. So if you could technologically handle it, it could solve all our energy problems in principle. The so-called Penrose process that Roger Penrose devised at the end of the 60s, and that seems to be also relevant for astrophysical black holes, for massive, supermassive black holes in the center of galaxies. So this we will do next time. So ergosphere and Penrose process. So for today, thank you again for listening, and bye-bye.